Hello and welcome. My name is Rafaelle E. Reyes and I will be discussing about the cardiac conduction system of the heart. We've learned from the previous lecture about the anatomy of the heart. Now let's focus more on this specific conduction system that consists of heart muscles and other conducting fibers that are specialized in initiating impulses and conducting them rapidly through the heart. So let's start with knowing what are the different components of the cardiac conduction system. We have four main components of this system, namely the sinoatrial node or the SA node, located at the right atrium of the heart, AV node or the atrioventricular node. This is located at the border of the atrium and the ventricle. Next to it is the bundle of His, which extends in the left and the right direction or the left and the right part of the heart, namely the left and the right bundle branches respectively. And this bundle branches form thin filaments that are called Purkinje fibers. If we isolate this conduction system, this is what we will see. Again, we have four components: the SA node, AV node, bundle of His, and the bundle branches, which forms thin filaments called the Purkinje fibers. Let's go now to the function of the cardiac conduction system. Why is this system important? First is the cardiac conduction system is responsible for the action potential generation in cardiac cells. I have here a graph of the action potential generation in ventricular cells with the action potential or the membrane potential at the y-axis and time at the x-axis. We learned from our molecular biology that action potential is the momentary reversal of membrane potential that is used in electrical signaling. And one thing to note about cardiac cells, they have this property called automaticity. It is the ability to spontaneously depolarize and generate action potential. This is the reason why, even if the nervous system is not functioning, our heart still beats. And even if we take out our heart, it will still beat for some time because it is electrically independent of the uh, nervous system and can spontaneously generate action potential for the contraction of heart muscles. Going back to this graph, we have four phases. Let's start with phase 4, which is the resting phase. In phase 4, uh, we have our membrane potential at negative 96 millivolts. We call this membrane potential as the resting membrane potential, which is usually negative for cells. So this resting membrane potential results from the influx of ions such as sodium and calcium, and also the outflux of ions such as potassium and chloride. These ions are regulated by pumps such as the sodium potassium pump, sodium and calcium exchanger, and others. Next to phase 4 is phase 0. We can observe in the graph that there's an increase in the membrane potential. This phenomena is called depolarization. It is a rapid positive change in voltage across cell membrane. The reason behind this is the increase in membrane conductance of sodium ions. So those sodium ions tend to go inside the cell, making the cell membrane potential more positive. After a brief increase in potential, we have phase 1. Phase 1 begins with the rapid inactivation of the sodium channels by the inner gate, reducing the movement of sodium into the cell. At the same time, the potassium channels open and close rapidly, allowing for a brief flow of potassium ions out of the cell, making the membrane potential slightly more negative. We can observe a slight decrease in membrane potential in phase 1 going to phase 2. And I would like also to mention that we have our threshold potential, which is around negative 40 millivolts. So before an action potential is generated, we have to overcome that threshold potential. And for ventricular cells, it's usually around negative 40 to negative 60 millivolts. So after phase 1 comes phase 2, which is called the plateau phase, due to the membrane potential remaining almost constant. So as the membrane potential, or as the membrane very slowly begins to repolarize, repolarization means it's becoming more negative. It's contrary to depolarization, which is the increase in membrane potential. So that's the difference between the two. Depolarization becoming more positive, meaning less negative. Repolarization, meaning it's becoming more negative, less positive. So at phase 2, the membrane potential very slowly begins to repolarize, as seen in the graph. And at phase 3, we can observe a rapid decrease in membrane potential. This is called the rapid repolarization phase. And after phase 3, we will go back to our resting phase, which is the phase 4. So that's the basic of the action potential generation uh, of ventricular cells that are regulated by the cardiac conduction system. Another important Another important function of the cardiac conduction system is its ability to regulate the pumping of blood through the heart. So here I have the requirements for effective pumping. First is a substantial atrial to ventricular delay. Second is the coordinated contraction of ventricular cells. And lastly, the absence of tetany. So I could explain these requirements more by showing you the next slide. First, let me show you how blood flows through the heart. Blood flows from the atria down to the ventricles, and we have these AV valves which open and close as blood flows through them. Now, if at first blood fills the right and the left atrium. Now, if the pressure here builds, uh, the blood will flow from the atria to the ventricle, forcing the atrioventricular valves or the AV valves to open. Now, as the blood flows, the pressure at the atria lessens and the pressure at the ventricles increases. So, as a result, this AV valve will close so that it will prevent the backflow of blood. Now, the cardiac conduction system is the one responsible for this mechanism. Once it uh, conducts electrical signals, the AV valve will either contract or will relax. That is one of the most important function of this conduction system to prevent the backflow of blood, because if blood if there's a backflow of blood, it will increase the blood volume in the atria or the ventricles, which can result to overworking and will ultimately lead to cardiac failure. Now let's go to the different major parts of the conduction system one by one. First, we have our sinoatrial node. It is a group of cells located at the wall of the right atrium of the heart. So it is made up of two words, sino plus atrial. So atrial meaning atrium and sino is right. Therefore, they are located in the right atrium of the heart. They can spontaneously produce an electrical impulse that travels through the heart via the electrical conduction system. It is to be noted that the electrical impulse causes contraction. So this is where all it originates. The electrical signal that flows through the heart or the cardiac conduction system starts from the sinoatrial node. In a healthy heart, the sinoatrial node continuously produces an action potential, setting the rhythm of the heart, and so is known as the heart's natural pacemaker. The main role of the sinoatrial node is to initiate action potentials so that it can pass throughout the heart and cause contraction. So remember, sinoatrial node is is where the electrical impulse came from. This graph is just showing you the action potential of a pacemaker cell, and the only thing that I would like to point out is that pacemaker cells don't have a flat resting face, unlike uh, what I've shown you earlier for ventricular cells. The reason behind is that uh, right after an action potential, our pacemaker cell will spontaneously uh, induce another action potential. So if our heart doesn't work this way, our heart will stop beating, or it will have large gaps between every beat. Next part of the cardiac conduction system is the atrioventricular node. It is in the border of the atrium and the ventricle, that's why it's called atrioventricular. It electrically connects the atria and the ventricles. And the main function of the atrioventricular node is to delay the impulses sent by the sinoatrial node by approximately 0.09 seconds. This delay in the cardiac pulse is extremely important. It ensures that the atria have ejected their blood into the ventricles first before the ventricles contract. This also protects the ventricles from excessively fast rate response to atrial arrhythmias. So just like what I've shown you earlier, that uh, the AV valves prevent the backflow of blood from the ventricles to the atria. So the atrioventricular node is the one responsible for controlling the opening and closing of those AV valves. This is the AV node. It is located at the border of the atria and the ventricles. That is why it's called atrioventricular. Now, this prevents the backflow of blood from the ventricles to the atria. Another major component of the cardiac conduction system is the bundle of His. As part of the cardiac conduction system, it transmits the electrical impulses from the AV node to the right and left ventricles. The bundle of His, a formed group of heart muscle cells, transmits the electrical impulses generated at pace intervals by the atrioventricular node to the right and the left ventricles. The signal is conducted via specialized channels which branch from the bundle of His and contact Purkinje fibers, which in turn signal the ventricles. As a result, the cardiac muscle of the ventricles contract. The bundle of His extends in the left and the right direction of the heart, and it gives rise to the filaments known as Purkinje fibers, which we will discuss later on. This is the bundle of His and extends on either the right part of the heart or the left part of the heart. If it extends in the right part, of course, it's called the right bundle branch. If it extends on the left, it's called the left bundle branch. And this bundle of His will ultimately form the Purkinje fibers, which is located at the apex of the heart. The bundle branches are also known as Tawara branches. They can either be left or right bundle branches, as I've illustrated earlier. They are offshoots of the bundle of His, and they transmit action potentials from the bundle of His to the Purkinje fibers. These structures lead to a network of thin filaments known as Purkinje fibers. So what are these Purkinje fibers? Uh, they are specialized conducting fibers composed of electrically excitable cells. Purkinje fibers allow the heart's conduction system to create a synchronized contractions of its ventricles and are therefore essential for maintaining a consistent heart rhythm. Conduct cardiac conduction potentials more quickly and efficiently than any other cells in the heart. And Purkinje fibers serve as the last resort when other pacemaker cells fail. So if the sinoatrial node fails to deliver an action potential, our Purkinje fiber will spontaneously produce its own action potential but is much weaker than what the sinoatrial node can produce. These are the Purkinje fibers located at the apex of the heart. Now, if the conduction system is cut off from the AV node, that means the sinoatrial node in the AV node cannot produce any action potential. The Purkinje fibers will produce their own, but the voltage is much smaller than what the sinoatrial node and atrioventricular node can produce. This figure is just showing you the different pacemaker rates of the structures of our cardiac conduction system. So, as I've mentioned a while back, the Purkinje network will produce its own action potential if the SA node or the AV node fails. Now, look at the pacemaker rate of the Purkinje network. It's only 25 to 40 beats per minute. It's much weaker than what the SA node can do because the SA node can beat for 60 to 100 beats per minute. Now let's go to how these cardiac potentials are measured. Of course, our device for this is the electrocardiogram or ECG or EKG. First point I would like to make is that ECG and EKG are the same. ECG stands for electrocardiogram and EKG stands for electrocardiogram, which is the German name for ECG. And the ECG originated from Germany. That's why it is originally known as EKG. But essentially, they are the same. ECGs measure electrical activity and collect data on the health and status of the heart. So what can ECG measure? We have our heart rate variability, stress, fatigue, heart age, breathing index, and sometimes mood. Here are the parts of an electrocardiogram. This is wrong. This should be cardiogram. We have our electrodes, amplifier, connecting wires, storage device, and transmission device. So we will go through these parts one by one. Electrodes are the actual conductive pads attached to the body surface. Uh, each electrode consists of an electrically conductive electrolyte gel and a silver-silver chloride conductor. Uh, Typically, we use 10 electrodes when conducting ECG, and the electrodes are attached to the limb, augmented limb, or the precordial or chest. This is what an electrode patch looks like. So this patch will be attached to our chest, to our limbs, and it will measure electrical conductivity. The most important component of an ECG is the amplifier. ECG amplifiers are needed to convert the weak electrical signal from the body into a more readable signal for the output device. So why is the amplifier so important? Remember, the electrical signal that we can detect from the heart is in the order of hundreds of microvolts. They are very weak. And so the amplifiers have the ability to strengthen the signals and convert them into a more readable signal. This is what a typical ECG reading looks like. It's divided into different intervals and different segments, and we also have our different waves. Now let's go to them one by one. For P wave, this represents the depolarization of the atria. So depolarization is the increase in voltage. Atrial depolarization spreads from SA node towards the AV node and from the right atrium to the left atrium. Next, we have our PR interval, which is measured from the beginning of our P wave to the beginning of the QRS complex. There, this is the uh, PR interval, and this PR interval uh, reflects the time the electrical impulse takes to travel from the sinus node to the AV node. Next, we have our QRS complex. The QRS complex represents the rapid depolarization of the right and the left ventricles. The ventricles have a large muscle mass compared to the atria, so the QRS complex usually has a much larger amplitude compared to those waves, compared to our P wave and our T wave. Next is the ST segment. The ST segment connects the QRS complex, this is our QRS complex, and the T wave. So it is measured from the end of the QRS complex to the start of the T wave. This represents the period when the ventricles are depolarized. Next and lastly, the T wave. This represents the repolarization of the ventricles. It is generally upright in all electrodes except a VR and a LED V1. These are types of electrodes. How do we interpret an ECG reading? So the output, which is the ECG reading, is usually shown like this. We can notice from the figure, we have our 3-second marks. One here, and the other is right here. So at this window, we have our 3 seconds. And at this window, we have another 3 seconds. And the most popular or the most common way of interpreting an ECG reading is what they call the 6-second technique, wherein they take the ECG reading for a full 6 seconds, then they count the number of or the number of QRS complex that can be found. Here we have our QRS complex. We have 1, 2, 3, 4, 5, 6, and 7. They take those QRS complex and multiply it by the factor of 10. This gives us our heart rate of 70 per minute. This is the easiest interpretation of an ECG reading. We have our different interpretations like the 3-second technique or other intervals. But for the sake of this video presentation, this is what we will use. Let me just clarify the different rows of the waves that I've showed you earlier. In P wave, this is our P wave. This represents the activation of the atria. So this is very important. It activates. This is the activation of the atria. This is by the action of our SA node. The QRS complex, the one with the highest amplitude of the waves, represents the activation of the ventricles. So the reason why it has a bigger amplitude compared to P wave and T wave is that the muscle mass here in the ventricles is much more larger than what can be found at the atria. And lastly, the T wave. T wave is the recovery wave. Now, on our right are the ECG outputs or ECG readings, and by comparing it to the normal heartbeat, we can see that when we have faster heartbeats, we have more QRS complex, or our they call it R wave. And when we have a slow heartbeat, we have less QRS complex. And for an irregular heartbeat, there is really no definite pattern. This is for arrhythmia, different regular heartbeats.